In my previous video, I have discussed the basic concept of limit and left-hand limit and right-hand limit. Now in this segment, I'm going to discuss the continuity of a function at a point. So let us start. Continuity of a function at a point. So let fx is a function then fx is said to be continuous at a point x is equal to a if left hand limit, which is written in abbreviation LHL, fx when x tends to a negative. X tends to a negative indicates the left hand limit. So this is the way to write it, is equal to right hand limit fx when x tends to a positive is equal to fa. Here fa is the functional value, that is the value of fx when x is exactly equal to a. So if this criteria is satisfied, we say that fx is continuous at x is equal to a. Now for better understanding, let us take an easy example. So suppose fx is given as x minus 1 when x is greater than 1, fx is equal to 0 when x is equal to 1, fx is equal to 1 minus x when x is less than 1. So now we have to check, the continuity of the function fx at x is equal to 1. So here I am going to explain the algorithm to find left hand limit and right hand limit. So first, left hand limit of fx, and here a is 1, that is the point at which we have to check the continuity. So x tends to 1 negative. Symbolically, left hand right is written as LHL fx when x tends to 1 negative, and to evaluate the algorithm is we write is equal to limit x tends to 1 minus h. Here h is a symbolic letter which stands for a value very close to 0, very small. So 1 minus h, and we write fx as it is. In the next step, we write limit x tends to 1 minus h, and 1 minus h is considered to be less than 1 when something is being subtracted from 1, though it is very small. The result is less than 1. So symbolically it is considered to be less than 1. So we see in our conditions, where is the condition x is less than 1. In front of it, what is the value of x given in the sum? So that is 1 minus x. That particular function we write here according to this. So 1 minus x we write. In the next step we write limit h tends to 0. This step is considered to be the step of transformation of limit, and this is the way to transform the limit, that when we write h tends to 0 instead of x tends to 1 minus h, this expression, this binomial, replaces the variable x in the function. So 1 minus h, so is equal to limit h tends to 0, then we open the bracket, 1 minus 1 plus h, 1 is cancelled, negative positive 1 cancelled out, and we get limit h tends to 0 h. Applying the limit, we get 0. So the value of left hand limit is 0. This is the algorithm to find out left hand limit. Now we are going to find right hand limit. So right hand limit RHL, that stands for right hand limit fx when x tends to 1 positive is equal to, we write limit x tends to 1 plus h, as we write in the case of left hand limit x tends to 1 minus h. In case of right hand limit, we write limit x tends to 1 plus h, and 1 plus h is considered to be something greater than 1. So in the sum we see the condition when x is greater than 1, and for that particular condition, what is the value of the function, that is x minus 1, that is written here, x minus 1. In the next step, we transform the limit as we have done in the case of left hand limit. We write x tends to 0 instead of x tends to 1 plus h, and then we replace x in the function by this binomial, whatever it is. So here it is 1 plus h, so 1 plus h will replace x in the expression. So 1 plus h minus 1. Here positive 1, negative 1 cancelled out, and ultimately we get limit h tends to 0 h again, and applying the limit we get 0. So the value of right hand limit is also 0. Now third, the functional value, that is fa. Here a is 1 as we have discussed, so f1 we have to find out, that is the function, the value of the function when x is exactly equal to 1, which is given already in the sum itself. When x is equal to 1, fx is equal to 0. So it is said to be the functional value of the function, so that is f1 is equal to 0, and this is already given in the sum. So this is equation number 3. So as we observe here, left hand limit we get 0, and here right hand limit is equal to 0, and the functional value is equal to 0. So from equation 1, 2 and 3, we get left hand limit of fx when x tends to 1 negative is equal to right hand limit of fx when x tends to 1 positive is equal to f1. So the criteria of continuity of the function is satisfied. So we say that function fx is continuous at x is equal to x is equal to 1, sorry. Fx is continuous at x is equal to 1. So this is the algorithm to check the continuity of a function at a given point. For more clarification, let us take another example. So the example is, suppose check the continuity of fx at x is equal to 0 when fx is given as e raised to the power 1 upon x minus 1 upon e raised to the power 1 upon x plus 1 when x is not equal to 0, and when x is not equal to 0 it means when x is greater than 0 or less than 0. For both the conditions the function has the same expression, and for x is equal to 0 function has the value 0, that is the functional value at x is equal to 0 is 0. So now we have to check the continuity of this function at x is equal to 0. So let us start with left hand limit. So left hand limit of fx when x tends to 0 negative is equal to limit x tends to 0 minus h. Functions is e raised to the power 1 upon x minus 1 upon e raised to the power 1 upon x plus 1. Next step is transformation of limit as we have discussed in the previous example. So when h tends to 0, we replace x by this binomial in the expression. So binomial is 0 minus h, that is minus h. So if we substitute x is equal to minus h in the expression, we have e raised to the power minus 1 upon h minus 1 upon e raised to the power minus 1 upon h plus 1. So limit h tends to 0, we may write e raised to the power minus 1 upon h as 1 upon e raised to the power 1 upon h minus 1 as it is, upon in the denominator also e raised to the power 1 upon e raised to the power 1 upon h plus 1. Now applying the limit, we have e raised to the power infinity, because e raised to the power 1 upon 0 is infinity, and e raised to the power infinity is infinity because something raised to the power infinity is infinity. So we write 1 upon infinity minus 1 upon infinity plus 1. When something is divided by infinity, we get 0. This is well known rule. So 1 is divided by infinity, we get 0 minus 1 upon infinity, again 0 in denominator plus 1. So we have minus 1 upon plus 1, that is minus 1. So let it be equation number 1. Now let us take right hand limit. Right hand limit of x tends to 0 positive is equal to limit x tends to 0 plus h. The expression function is e raised to the power 1 upon x minus 1 upon e raised to the power 1 upon x plus 1. Now next step, the transformation of limit h tends to 0, and in this step we replace x by this binomial, that is 0 plus h, that is only h. So we have in the expression e raised to the power 1 upon h minus 1 upon e raised to the power 1 upon h plus 1. Since if we substitute h is equal to 0 in this expression, we have infinity minus 0, that is infinity, upon infinity plus 0, that is also infinity. So infinity upon infinity we get, which has no value, that is considered to be meaningless in maths. So we have to do something else. So let us divide the numerator and denominator by e raised to the power 1 upon h. We have 1 minus 1 upon e raised to the power 1 upon h, because if we divide e raised to the power 1 upon h by e raised to the power 1 upon h, we get 1 minus, we divide 1 by e raised to the power 1 upon h, we get 1 upon e raised to the power 1 upon h. Similarly, in the denominator we have 1 plus 1 upon e raised to the power 1 upon h. So now if we apply the limit in this expression, we have 1 minus 0. Why? Because 1 upon infinity is 0, as we have done in left hand limit, upon 1 plus 1 upon infinity, that is also 0. That is, we have 1 minus 0, that is 1, upon 1 plus 0, that is 1. 1 upon 1 is equal to 1. So if we compare the left hand limit and right hand limit's value from equation number 1 and 2, we get both have different values. Left hand limit is equal to minus 1 and right hand limit is equal to plus 1. So left hand limit of fx is not equal to right hand limit of the function at x is equal to 0. From 1 and 2 we get left hand limit of fx when x tends to 1, 0, negative is not equal to right hand limit of fx when x tends to 0, positive. So fx is discontinuous because the criteria of continuity is not satisfied. So fx is discontinuous at x is equal to 0. Hopefully you might have understood the concept of continuity of a function at a point, and if you like this video, please share it on your social networks and give a thumbs up. Thank you.